Okay, good evening everyone. I'm Anesh Ambekar, PMRF and PhD candidate from Aerospace Engineering ISC Bangalore. Welcome to this week's live interaction for the NPTEL course Engineering Mathematics 2. This course is being conducted by Professor Jitendra Kumar from IIT Kharagpur, and the course code is NOC 23 MA 25. In this interaction, we'll be covering the content. We'll be discussing some problems related to the content covered in week 7. So that included Fourier series. Like it's initially started with definition of periodic functions. What is orthogonality? Then what is a trigonometric series and how they are orthogonal? What is a piecewise continuous function? Then the condition for a Fourier series to exist on a particular periodic function, whether it has on different periods, say like 2 pi or 2L. We also looked at some convergence theorems, specifically the Dirichlet theorem, which which establishes how the Fourier series converges to a particular point x. Then in convergence, we studied three types of convergence notions, which include mean square convergence, point-wise convergence, and uniform convergence. At the very end, we touched upon what are even and odd functions and how their nature affects the coefficients of the Fourier series. With this in mind, we'll move to this week's set of curated problems. So the first problem deals with the concept of periodic function. So it asks us what is the fundamental period of the function f of x equal to cos of mod of x. Okay, so the definition of fundamental period is f of t plus x is equal to x, where t is the smallest possible period. When t is the smallest possible period, we call it fundamental period. For the question that is given here, f of x equal to cos of mod of x. If we were supposed to plot this, so cos of mod of x means that this basically means that f of minus x is nothing but cos of mod of minus x, which is again cos of mod of x. So this is nothing but f of x. So we are the function f of x that we are given, we can say that it's an even function. This is -1, this is 1. And if you are now to plot cos of mod x, start from 1, go to 0, go to -1, again go to 0, again +1, and so on. This is how it will look on the right, positive x half, and on the negative x axis, we would see the same thing mirrored. But if you think about it, this is actually nothing but f of x is nothing but cos of x only. So for cos of x, we know that the period is 2 pi. So fundamental period is 2 pi. So if I do f of x plus 2 pi, that is nothing but cos of mod of x plus 2 pi, which is nothing but cos of x. So from this graphical plot, or a graphical diagram rather, we can see that intuitively f of x equal to cos of mod x is nothing but cos of x itself, which is why the fundamental period ends up being 2 pi. We now move to the second problem. It deals with the concept of orthogonality. But before we go there, let us look at what exactly is being asked. We are asked to integrate cos of mx, cos of nx, where m and n are both integers but they are not equal, and over the over x going from minus pi to pi. So cos of mx into cos of nx is nothing but half of cos of m plus n into x plus cos of m minus n into x. With this in mind, our integration essentially becomes integration over minus pi to pi, half of cos of m plus n into x plus cos of m minus n into x dx. Notice that since m is not equal to n, this m minus n term is non-zero. So we have integral half of cos of k1x dx plus half of integral minus pi to pi cos of k2x dx, which we know that both of these integers will vanish, but if you were to write it out explicitly, it would be sine of minus pi to pi plus 1 by 2 k2 sine of 2x limits from minus pi to pi. I'll just write it, k1 is m plus n and k2 is m minus n. With this in mind, we know that sine of multiple of any integer, sine of n, sine of say, sine of kx is equal to 0 when k is an integer and x belongs to, and x is basically pi. So sine of k pi, we know that it's 0. We basically use this to substitute here, and we'll essentially end up with 0 plus 0. So this particular integral has the value of 0, and this touches upon the important concept of orthogonality. Suppose you have two functions, phi of x and psi of x, for x belonging to a to b, then they are called orthogonal if integral phi of x psi of x dx over the range a to b goes to 0. This orthogonality is a very useful property when we look at when we look to approximate a function using Fourier series. So the terms of Fourier series essentially end up having trigonometric series which are orthogonal, which turn out to be orthogonal over this range. Now we are given the third question. So this is about Fourier series, where we are told that a function f of x is expressed in the Fourier series. F naught goes to alpha by a naught by 2 plus summation n equal to 1 to infinity a n cos nx plus b n sin nx. And we are asked to find the value of a naught. And we are given that f is a periodic function with the following data. So if I am to look at f of x, so x can go from minus pi to, so this is my y, this is minus pi, this is pi, this is my x-axis, and this is pi, this is 2 pi, So our function essentially goes from this to this, and then it goes from this to this. Oh, sorry. It goes to 0 in the other half, in the positive. What this would look like is 2 pi plus x at x equal to minus pi is nothing but pi. And when x equals 0, 2 pi plus x is 2 pi. When x is between 0 to pi, the function essentially lies on the x-axis. So this is what we have been given. It is a piecewise continuous function, and we do know that if f of x is piecewise continuous function, then this implies that Fourier series can exist. And we are asked to calculate the value of a naught. So if you remember the formula, a naught is nothing but 1 by pi integral minus pi to pi f of x dx, which ends up being 1 by pi. So we have to do two integrations, minus pi to 0 to pi plus x dx plus integral 0 to pi, this is 0 dx. So this is 1 by pi times the first, so this term will identically will end up going to 0, and this term becomes 2 pi x plus x square by 2 from minus pi to 0, which is 1 by pi times. So for 0 the term is 0, for minus pi it is minus 2 pi square plus pi square by 2, which turns out to be 1 by pi into 3 pi square by 2, which is 3 pi by 2. So we end up with option B. Problem number 4. It's a true or false question, and it has the statement Fourier series of piecewise continuous function over a closed interval minus pi to pi never exists. So this statement is false. The reason is sufficient condition for Fourier series is the sufficient condition for Fourier series. This is nothing but f of x needs to be piecewise continuous function. If this is satisfied, we can write a Fourier series. Problem number 5. F of x can be expressed in Fourier series. F naught goes to alpha a naught by 2 plus summation n equal to 1 to infinity an cos nx plus bn sin nx. And we are asked to calculate the value of an of the Fourier series of periodic function f with period 2 pi in minus pi to pi. Okay, I have made a mistake here also. Actually, minus pi to pi. And the function f of x is given as follows. So I'll just plot it for convenience. This is y, this is x, this is 0, this is origin, this is minus pi, this is plus pi. When x is between 0 to pi, y takes a value k. When x is between 0 to minus pi, y takes a value minus k. So straight away you can see that this is an odd function. So what that means is f of minus x is nothing but minus of f of x. You can see that if suppose your x is positive, then your value comes here, f of minus x would come here, and it's minus k, which is minus of f of x. So this basically tells us that f of x is an odd function. And for an odd function, now we are asked to calculate the coefficient an. So an is coefficient of cos of nx. So if you remember the formula, it is nothing but an is equal to 1 by pi integral minus pi to pi f of x cos of nx dx. Now we know that f of x is an odd function, but cos of nx is an even function. Therefore, this overall product is an odd function. And if we are integrating it from minus pi to pi, essentially the integration that we do from minus pi to 0 will cancel out the integration that we do from 0 to pi. So for our case, an will turn out to be 0. If I am to write this in the like all the steps for this particular problem, it essentially is I times an is integral of minus pi to 0 k into cos of nx dx minus k into cos of nx dx plus integral 0 to pi k into cos of nx dx. For the first integrand, I'll just change the limits. So this essentially becomes minus integral 0 to minus pi minus k, or what I think what might be more straightforward is to simply integrate it. So that would turn out to be minus k by n sine of nx minus pi to 0. You can see that these terms will both vanish to 0. K by n sine of nx. Again, these two terms will also go to 0, both the limits. So this essentially whole thing goes to 0. This also goes to 0 in both limits. So my pi an is 0, which means that my an should be 0. So this is how you could write it in like this whole steps, but this approach is preferable. Wherever if you have f of x being odd or even, you can quickly check how their product looks like. You can check the range where it's being integrated, which is minus pi to pi in our case, and from that you can directly conclude if a particular coefficient would go to 0. Problem number 6. Let f of x be expressed in Fourier series. F naught goes to a naught by 2 plus summation an cos nx plus bn sin nx. And we are asked to calculate the value of bn of the Fourier series of the periodic function f with 2 pi period. So for our case, this is x, this is y, and f of x goes to, suppose this is minus pi, this is pi, this is pi, this is 2 pi, minus pi minus 2 pi. So f of x goes to like this, then another like this. This is at 2 pi, and another like this, and this is at minus 2 pi, and so on. So this is a periodic function f of x, and we are asked to calculate the coefficient of the sine term bn. So with this in mind, we calculate bn pi times bn is integral from minus pi to pi 2x into cos of, sorry, sine of nx dx, which is nothing but 2x into minus cos of nx by n. I am integrating by parts, plus integral minus pi to pi 2 times of minus cos of nx by n dx. So which is 2x times minus cos of nx by n, limiting from limits minus pi to pi, plus minus 2 by n integral minus pi to pi cos of nx dx. This term should go to 0 because it's an integration of cos from minus pi to pi, and thus our term becomes pi bn is equal to 2 pi into cos of into 2 pi by n into minus cos of n pi. So cos of n pi is nothing but minus 1 raised to n plus minus 2 pi by n times minus of minus 1 minus cos of minus n pi, nothing but cos of n pi. So that should be minus of minus 1 raised to n, which essentially gives us pi bn to be equal to 4 pi by n into minus 1 raised to n plus 1. Cancelling out pi, bn turns out to be 4 by n times minus 1 raised to n plus 1, which is option D. Problem number 7. Let f of x be expressed in the Fourier series with this particular form: a naught by 2 plus summation a n cos nx plus b n sin nx. And we are asked to calculate the value of a naught for given the function f of x. So a naught is pi times a naught is integral of f of x dx from minus pi to pi, which is, so minus pi to 0 is just 0, 0 to 1 is 1, and 1 to pi is again 0. So 1 times dx is x with limit 0 to 1, which is nothing but 1, which simply gives us a naught to be equal to 1 by pi. So option number D. Problem number 8. So now we are given a function f of x, which is defined as follows: f of x equals minus pi by 2 when x is between minus 1 to 0, and it equals x plus pi by 2 when x is between 0 and 1. And we are asked to calculate the value of Fourier series, the value at which Fourier series of f will converge when x is equals minus 1. Okay, so we first note that the function f of x, I'll just first plot f of x, I think that's easier. So we have minus 1 to 1, this is my x axis, this is my y axis, and x is between minus 1 to 1, minus 1 to 0, this is minus pi by 2 when x is between 0 and 1, this is pi by 2 and pi by 2 plus 1. So this gives us our function f of x, and we will make a few observations. Firstly, f of x is piecewise continuous function. Secondly, for f of x, one-sided derivatives exist. What this would allow us to say that f the Fourier series of x, this basically tells us that the Fourier series of f of x will essentially converge in a pointwise sense to f of x positive So f of x negative by 2. In this case, f of minus 1 coming from the positive side, coming from the right hand side of minus 1 is nothing but minus pi by 2, and f of minus 1 coming from the negative side. So we want to look at the negative side of this. So if f of x being modeled by Fourier series, this would essentially look at it like a periodic function, and therefore f of at minus 1, if we want to look at it, the value coming from its left hand side, it's essentially the value at the other limit, which is 1 plus pi by 2, and therefore our Fourier series would converge to 1 plus pi by 2 plus minus pi by 2 whole by 2, which is nothing but half. So option number B. So this problem basically touches upon convergence criteria, specifically the point-wise convergence criteria, and it requires that f of x be not only be piecewise continuous but also have one-sided derivatives, which is what exists for this particular function f of x. Next, we go to problem number 9. So in problem number 9, we are given a sequence u of whose nth term is un is equal to sine raised to n by sine raised to nth sine of x whole raised to n by n, and we are asked to comment on whether this sequence converges or whether it converges uniformly or something like that. You can quickly note that the modulo of un, which is nothing but nth power of sine x by n, will always be less than or equal to 1 by n, because modulus of sine of x is always less or equal to 1. So this is true for all x actually. So we assume epsilon to be equal to 1 by n, and let capital N equal to n. What this tells us that modulo of un minus 0 is less than epsilon for all n greater or equal to n of epsilon. So which is nothing but 1 by epsilon. So what does this tell us? This tells us that as the number n goes on increasing, un will keep on becoming smaller and smaller till it converges to 0, and it will be always be within the neighborhood of 0 by a certain number epsilon, which is given by 1 by n, and therefore if you therefore not only un converges, but un also converges uniformly. By uniformly we mean that the number capital N, the number capital N for which un will always satisfy un minus 0 less than epsilon is independent of x. So this is independent of x and only depends on epsilon. So no matter what x value you choose, this will always converge and converge uniformly. So this covers the another criteria of convergence. And finally, we have another function f of x is minus 2 pi when x is between minus pi and 1. This is pi, this is 2 pi. This is minus 2 pi, and then it increases like this. It goes up to a maximum value of pi minus 1. And we are asked to comment what happens, how does the Fourier series converge. Again, we'll make the observations about f of x, And first observation is that it is obviously piecewise continuous function, which is which means that Fourier series can exist. And the second observation is that one-sided derivatives exist, which means that Fourier series of f of x will converge to f of x plus f of x minus by 2 in a pointwise fashion. In our case, this turns out to be f of 1 plus is nothing but limit x tends to 1 positive f of x. So that is limit x tends to 1 from the positive side, x minus 1. So this is 0. And similarly, if you look at 1 minus, it is limit x tends to 1 from the left side, f of x, which is minus 2 pi. Therefore, our converged value is minus 2 pi plus 0 by 2, which is minus pi. So this way we obtain the converged value. So this covers the problems that I had for this particular week. If there are no more doubts, we, then we'll close this session. We'll meet again in the next week for the next interaction.